This is SpaceTime Series 24, Episode 118, for broadcast on the 18th of October 2021. Coming up on SpaceTime, plans announced for an Aussie Lunar Rover, astronomers conduct a supernova post-mortem, and a new hypothetical protoplanet. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
NASA has asked the Australian Space Agency to develop a robotic rover to find, study and transport regolith on the lunar surface. The rover will be designed, built and tested in Australia before being transported to the United States for launch. The microwave oven-sized vehicle will work as part of a NASA-operated in situ resource utilisation project. The mission, which will launch in 2026, will collect regolith for processing by equipment aboard the lander in order to demonstrate the ability to extract oxygen from locally sourced material on the Moon. Lunar soil contains oxygen in the form of chemical compounds with elements like iron and silicon. This small-scale technology demonstration will aid in the design of larger, more capable units in the future. Long-term plans include converting lunar water ice deposits into its hydrogen and oxygen constituents for use as rocket fuel, as well as providing crews with air to breathe and water to drink. Other experiments will eventually see lunar regolith processed into construction materials on the Moon. It's all part of the extended Artemis mission, which will see humans return to the lunar surface in 2025 and eventually use the Moon as a jumping-off spot for missions to Mars and beyond. The Australian-developed rover is part of Canberra's $150 million Moon to Mars initiative announced by Prime Minister Scott Morrison at NASA headquarters in Washington in 2019, with the primary aim of boosting growth in the Australian space sector and at least tripling its current size.
Space has captured our imagination for generations. In 1969, we helped the world watch on in awe as America put man on the Moon.
That's one small step for man, one giant leap for mankind.
Now, as we look to the future, the world will watch us make history of our own. Australia. We're going to the Moon.
This is SpaceTime. Still to come, astronomers conduct a supernova post-mortem and a new hypothetical protoplanet. All that and more still to come on SpaceTime. Astronomers have delved deep into the remains of a thermonuclear supernova explosion. The new data, reported in the Astrophysical Journal, has allowed scientists to study in incredible detail the devastated remains of the progenitor white dwarf star which triggered the blast. White dwarfs are among the most stable of stars. They're the cause of sun-like stars which have reached the end of their lives. Stars shine by fusion of hydrogen into helium in their core. And when they start to run out of core hydrogen and the fusion process begins to stop, gravity starts to take over and the star begins to contract. And this contraction eventually increases core temperature and pressure sufficiently for the core helium to begin to fuse into carbon and oxygen, while at the same time a shell of hydrogen begins burning outside the core. And that causes the star's outer gaseous envelope to expand. That expansion means the surface of the star's gaseous envelope is now further away from the contracted core, and so it cools down, turning the star into a red giant. When our Sun reaches this stage of its life in around 7 billion years from now, its surface will have expanded out to engulf Mercury, Venus, and most likely the Earth as well. Eventually, the doomed star runs out of core helium to fuse, and as it's not massive enough to fuse heavier elements together, the star effectively dies. Its bloated outer envelope floats away as a spectacular cloud called a planetary nebula, exposing its white-hot stellar core as a white dwarf, a superdense object about the size of the Earth. Astronomers think about 97% of all stars in the universe will become white dwarfs. However, not all of them survive. See, a white dwarf in a binary system with a nearby companion star can become a sort of cosmic powder keg. If the companion's orbit brings it too close, the white dwarf's intense gravity can pull material off the companion star. This material then builds up on the white dwarf until it reaches a tipping point, known as the Chandrasekhar limit, about 1.44 times the mass of our Sun. And once the white dwarf passes this limit, it becomes so unstable it triggers a spectacular stellar explosion called a thermonuclear or Type 1a supernova, blasting the star to pieces. Now, while it's generally accepted that such encounters between white dwarfs and companion stars are one likely source for thermonuclear supernova explosions, many details of the process aren't well understood. And one way to investigate the explosion mechanism is to go sifting through the debris and ejecta left behind by the supernova. And that's what the authors of this report did. They used radio observations from the CSIRO's Australia Telescope Compact Array at Narrabri, the National Science Foundation's Very Large Array in the United States, together with NASA's Chandra X-ray and Spitzer infrared space telescopes to study G344.7-0.1, a supernova remnant located some 19,600 light-years away. The X-ray observations by Chandra were key to the study. That's because X-rays are one of the best ways to study supernova remnants and measure the composition and distribution of the metals they contain. Astronomers refer to all elements other than hydrogen and helium, the elements generated in the Big Bang 13.8 billion years ago, as metals. Astronomers estimate that G344.7-0.1 is somewhere between 3,000 and 6,000 years old. On the other hand, the most well-known and widely studied thermonuclear supernova remnants, such as Kepler, Tycho and SN 1006, all exploded within the last 1,000 years or so. Therefore, this deeper look into this much older supernova remnant with Chandra gives astronomers a window into an important later phase in the evolution of these events. Both the expanding blast wave and the stellar debris produce X-rays in supernova remnants. As the debris is moving outwards from the initial explosion, it collides with surrounding interstellar gas and dust, causing it to slow down. And this creates a sort of reverse shock wave, travelling back towards the centre of the explosion like an echo. And as it travels back towards the source, it's slamming into debris still on the outward journey, causing that debris to heat up to millions of degrees and making it glow in X-rays. Now, thermonuclear supernova remnants like Kepler, Tycho and SN 1006 are still too young for the reverse shock front to have time to plausibly travel backwards to heat all the debris in the remnant's centre. However, the relatively advanced stage of G344.7-0.1 means that reverse shock front has already moved back through the entire debris field. That's lit up the debris, and that's let scientists see what's going on. The Chandra data is showing X-ray emissions from iron and silicon, with the region with the highest density of iron surrounded by arc-like structures containing the silicon. Similar arc-like structures were also found for sulfur, argon and calcium. The Chandra data also suggests that the region with the highest density of iron has been heated by the reverse shock front more recently than the elements in the arc-like structures, implying that this is located near the centre of the stellar explosion. The findings support predictions for models for thermonuclear supernova explosions, which show that heavier elements are produced in the interior of an exploding white dwarf. Interestingly, however, the data also shows that the densest iron is located to one side of the supernova remnant's geometric centre. The authors think this asymmetry is likely being caused by gas surrounding the remnant being denser on one side than the other. An interesting puzzle for pondering. This is SpaceTime. Still to come, a new hypothetical protoplanet, and space, the final frontier. All that and more still to come on SpaceTime. A team of planetary scientists have come up with something new to look for in the heavens, which they're calling a synestia. A huge, and at this stage still hypothetical, spinning donut-shaped mass of hot vaporized rock formed as planet-sized objects smash into each other. Now, if their hypothesis is correct, at some point early in its history, some 4.6 billion years ago, our Earth too was likely a synestia. The objects, described in the Journal of Geophysical Research Planets, are proposed by planetary scientists Simon Locke from Harvard University and Sarah Stewart from the University of California, Davis. Current theories for planetary formation propose that rocky planets such as Mars, the Earth and Venus were all formed early in the existence of our solar system as smaller objects collided together. These collisions were so violent the resulting bodies melted and partially vaporized, eventually cooling and solidifying into the nearly spherical planets we know today. But of course, a rotating object has angular momentum, and that needs to be conserved in a collision. Locke and Stewart suggest that when you think of angular momentum, you should be thinking of a skater spinning on ice. If she extends her arms, she'll slow her rate of spin, and to spin faster, she holds her arms in close. But her angular momentum remains the same. Now consider two skaters turning on ice. If they catch hold of each other, the angular momentum of each adds together, so their total angular momentum remains the same. Locke and Stewart modelled what happens when the ice skaters are Earth-sized rocky planets, colliding with other large bodies with both high energy and high angular momentum. They looked at the statistics of giant impacts, finding that they can form a completely new structure. The authors found that over a range of high temperatures and high angular momentum, planet-sized bodies could form a new, much larger toroidal structure, an indented disk, sort of like a donut with the centre filled in. The object is mostly vaporized rock with no solid or liquid surface. And the authors named their new object as synestia, from syn, meaning together, and hestia, the Greek goddess of architecture and structures. The key to synestia formation is that some of the structure's material actually goes into orbit. In a spinning solid sphere, every point from the core to the surface is rotating at the same rate. But in a giant impact, the material of the planet can become molten or gaseous and expand in volume. And if it gets big enough and is moving fast enough, parts of the object will pass the velocity needed to keep material in orbit, and that's when it forms a huge disc-shaped synestia. Most hypotheses suggest that giant impacts cause planets to form a disk of solid or molten material surrounding the planet. But for the same massive planet, a synestia will be much larger than a solid planet with a disk. The authors suggest that most planets likely experience collisions that could form a synestia at some point during their formation. They propose that for an object like, say, the Earth, the synestia wouldn't last very long, perhaps 100 years or so, before it lost enough heat to condense back into a solid object. But they propose that synestias formed by larger or hotter objects, such as gas giants or even stars, could potentially last much longer. The synestia structure doesn't suggest new ways to think about the Moon's formation. The Earth's moon is remarkably similar to the Earth in composition, and most current theories about how the Moon formed involve a giant impact between the proto-Earth and a Mars-sized planet called Theia, which caused both bodies to melt together and threw a lot of material into orbit, which eventually coalesced to form the Moon. But such an impact could theoretically instead have formed a synestia, from which the Earth and Moon both condensed. Planetary scientist Dr. Simon O'Toole from Macquarie University says no one's actually observed the synestia directly.
And so basically it's this kind of body that you get immediately after the collision between two planets, as we currently understand them, two planet-sized objects. So part of this is driven by the formation, how did the Earth's moon form? The basic idea is that you had two planetary-sized objects that collided. And they've done some theoretical calculations that where they've done all these, they basically collided two planetary mass objects together and to see what would happen. And one of the outcomes seems to be that you get, rather than getting an Earth and a moon like we have, is you get sort of this very large donut of hot vaporized rock that is sort of spinning around, a very, very, very large, much bigger than, say, the actual two planets, because you've got this vaporized rock in a sort of astronomers would probably call it a torus, which is really a fancy name for a donut. And you'd have some central region which was more dense, and then this vaporized sort of this cloud of material going around in a donut shape around the outside. And it's sort of unclear to me how long this could persist, how long the before it sort of started either dispersing or just collapsing, because, angular momentum is the key here. And in these sorts of situations, we don't really understand angular momentum very well, in my opinion. So it's a very, very interesting idea, this synestia idea. I'm not really keen on the name synestia, but, that it is what it is. But I like the concept that it could happen. The one key part here is this is very, very theoretical. No one has observed anything that looks like this, and that's in part because it's very, very difficult, because the scale here is still only a little bit larger than a planet, maybe out to the orbit of the moon or a bit beyond. So it's very, very difficult to observe this kind of thing.
When we look at planets that appear to have rings around them, that's what they have. They have rings around them. They all the gas giants do, and we assume the Earth did when Theia slammed into it and the moon resulted. Could it have been a synestia rather than a ring, or is a synestia really just a fat ring?
Well, I'd say that the rings are more likely the debris left over from the formation of the giant planet's moon. So the planet itself formed, the giant planet formed at the center, and then there's a whole lot of other material around the outside, and then it gradually accreted into the various moons, and then there were any sort of leftover material went into the rings. Although, of course, Saturn is a little bit different because it's in fact fed by a geyser from one of its moons.
Enceladus,
the rings are continuously being renewed, but certainly, I think that any ring structure is quite different to this, because even if you had a collision, although I think when we've looked at comets and that sort of thing that have collided into Jupiter, run into Jupiter, they've basically been just destroyed completely. But that's because you have a very large thing with a very, very small thing, whereas in this scenario, you're looking at Earth-sized objects. You're looking at something like Mars and something like Earth, that sort of ballpark colliding, and they're very rocky. So I think that has a big impact on the outcome.
So this really means that the existence of a synestia would depend very much upon which eventual model of planetary formation turns out to be correct.
Yeah, it does. It does. I mean, I sort of feel like the various models of planet formation probably occur, just depends on their initial conditions. So that's a hunch. I wouldn't call that backed up by anything, but that's my hunch, is that they both will work in the right scenario. Planetary accretion model is basically where the star forms at the center of a very large cloud of gas and any other material, rock, whatever, and it forms you have this very large collapse of material, and then you get the nuclear ignition, same as your star, and then any material left over starts rotating around that star, starts orbiting it, and then eventually you get little impacts and collisions, but the bits of material there, the rock and gas and ice and whatever, collide and stick together and gradually accrete, become larger and larger, and as they become larger, they attract more material, and so they eventually become what you would call a planetesimal, so a small planet, and they get bigger and bigger and bigger. And in the case of gas giants, the idea is you might have some dense core of material, but then you get gas that just gets sort of drawn to it and accretes onto that. In the case of the terrestrial planets, the rocky planets, it's just rock and maybe ice and that kind of thing, but the ice is obviously going to be vaporized, and so you just have this molten thing, because as they collide, as all of the bits and pieces collide, they get very, very hot. And so that sort of does feed into this synestia idea, in the sense that you have these two hot things that collide, and then they spew out this large amount of hot vaporized rock. The other model is the gravitational instability model of planet formation, and that's much more where, rather than the accretion, you have it forms. It's a little bit more like star formation. You get regions of high density that sort of collapse in on themselves, and I think that, my personal, once again, it's more a hunch, but I think that might match brown dwarfs a little bit better.
It does, yeah. The latest evidence we're getting from jets coming out of brown dwarfs, almost a light year long, indicate that that model may well be correct, at least for brown dwarfs, which sort of fill that gap between the largest planets and the smaller stars.
Yeah, and that actually changes our ideas of, is something like Jupiter a failed star or a failed brown dwarf, because if it formed through an accretion mechanism rather than gravitational instability, then it's probably more just a very large planet, whereas a brown dwarf that formed potentially by the gravitational instability is much more like a failed star.
How does synestia fit in with those two models?
Well, basically, the synestia fits in much better with the accretion model, I think, because you have these two rocky objects that impact each other, and then they spew out this large, very vast cloud of hot vaporized rock, and that forms, this sort of donut-shaped cloud that orbits the central core of whatever's left over from the collision, from the impact. I think it fits in better with when you're looking at rocky planets rather than sort of gas giants.
That's planetary scientist Dr. Simon O'Toole from Macquarie University. And this is SpaceTime. Still to come, Space the Final Frontier, and Phase 1A and B Australians being advised to get a booster third COVID-19 vaccination shot. All that and more still to come on SpaceTime.
Space, the final frontier. These are the voyages of the starship Enterprise. Its 5-year mission: to explore strange new worlds, to seek out new life and new civilizations, to boldly go where no man has gone before.
See the blue cover go whip by, and now you're staring into blackness. That's the thing. The covering of blue, this sheet, this blanket, this comforter of blue that we have around. We think, oh, that's blue sky, and then suddenly you shoot through it all of a sudden, as though you whip off a sheet off you when you're asleep, and you're looking into blackness, into black ugliness, and you look down, and there's the blue down there, and the black up there, and it's just, there is Mother and Earth and comfort, and is there death? I don't know. Is that death? Is that the way death is? Whoop! And it's gone. Jesus. It was so moving to me. This experience has been something unbelievable. You see, weightless, my stomach went up, and I thought, this is so weird. But not as weird as the covering of blue. This is what I never expected. Oh, it's one thing to say, the sky and the thing and the fragile. It's all true. But what isn't true, what is unknown until you do it, is there's this pillow, there's this soft blue. Look at the beauty of that color. And it's so thin. And you're through it in an instant. So you're through 50 miles, whatever the mathematics
fast.
is.
Yeah, really fast.
It's like a beat, and suddenly you're through the blue. And you're into black. And you're into, it's mysterious and galaxies and things. But what you see is black. And what you see down there is light. And that's the difference. Is the most profound experience I can imagine. I'm so filled with emotion about what just happened. It's extraordinary. I hope I never recover from this. I hope that I can maintain what I feel now. I don't want to lose it. It's so much larger than me and life.
I hope I never recover from it. They were the words of a highly emotional William Shatner following his journey to the edge of space aboard Blue Origin's New Shepard. It was the second manned flight for the space tourism venture, and the inclusion of James T. Kirk, captain of the Starship Enterprise in the Star Trek franchise, ensured global coverage. For Shatner, seeing how thin the Earth's life-giving atmosphere was, and how quickly one passes through its protection on the way to the blackness of space, was a profound life-changing experience. The 11-minute suborbital ballistic journey reached an altitude of 106 kilometers.
All right, everybody. Chris Blosshausen, Glenn DeVries, Audrey Powers, and William Shatner are about to go where very few humans have gone before. Ladies and gentlemen, it's time to launch this rocket. Godspeed, New Shepard.
-10, 9,
8, 7, 6, 5, 4. Command engine start. 2, 1.
Has cleared the tower. She is on her space with the second human spaceflight crew. What a launch. We are on our way to Max Q, the first milestone here on its flight to space. We have confirmed Max Q. This is when the aerodynamic stresses on the vehicle were at their maximum. New Shepard's second human flight with Audrey Powers, William Shatner, our customers Glenn DeVries and Chris Bosshausen on board. They are well on their way to space. So far, a nominal flight, a clean burn on our Blue Engine 3. New Shepard giving them a beautiful flight to space this morning. The rocket is climbing towards an altitude. We're aiming just over the Kármán line, the internationally recognized line of space of 100 kilometers. That is about 328,000 feet. And now we've had main engine cut off. The BE-3 engine has shut off. And in just a moment, we're going to separate the capsule from the booster. And at that point, our astronauts will have the opportunity to get out of their harnesses and enjoy the beauties of zero-G. Clean separation between the capsule and the booster. They are continuing their ascent over the Kármán line, and there they are, over 328,000 feet, over 100 kilometers. Welcome to space. The newest astronauts on board our crew capsule just about hit their apogee at about 351,000 feet. So far, a nominal flight for our second human crew. So exciting, Jackie, to have sent Captain Kirk himself, William Shatner, to space, as well as our two customers, Chris Bosshausen from Australia, to all the fans tuning in from down under. A big shout out to you guys, as well as Glenn DeVries and our very own Audrey Powers. They are coming back home. The booster, of course, is going to beat the capsule back home. It is more aerodynamically shaped, of course, at the base of the capsule. It's kind of a blunt end, so it's less aerodynamic. What we're going to see coming up shortly is at the top of the rocket, we have the ring fin. There is some what we call the pie fins that extend from the ring fin, as well as the drag brakes. The pie fins, the wedge fins, help stabilize the vehicle, kind of like the feathers at the back of an arrow. And then the drag brakes, it cuts the velocity dramatically. The wedge fins are out. The descent, we are going to expect the BE-3 engine to relight just at about 3,600 feet or about 1,200 meters above ground level. Let's wait for that now. The drag brakes have deployed. And here we come, New Shepard. And touchdown. Welcome back, New Shepard. The fourth flight to space and back for that vehicle provided a beautiful flight to space for our second human crew. Wow, that gets me every time we do this live down here in Texas. The sonic boom is so cool. Drag brakes are folding back in, as have the wedge fins. Just looks like you could fuel her up and go again. What do you think, Jackie?
And even when you know to expect the sonic boom, it still catches you off guard every time.
Talk about a rumble. New Shepard rocket there in the West Texas desert. But of course, the show is not over. The capsule is descending. We are waiting for first the drogue chutes to deploy. Those are very much like the guide parachutes. They will subsequently be followed by the main parachutes that will first reef and then fully inflate. And there go the drogue parachutes. And here come the mains. Whew, what a flight. You can already start to hear the cheers from outside our stage here in West Texas. And here comes our crew back into the desert.
Newest astronauts 596, 97, 98, and 99.
Stand by touchdown. Stand by touchdown.
And capsule touchdown. Welcome back, the newest astronauts. Audrey Powers, William Shatner, our customers, Glenn DeVries, and Chris Bosshausen. What a day for you. Welcome back.
This is SpaceTime. And time now to take a brief look at some of the other stories making news in science this week with a science report. The Australian Technical Advisory Group on Immunisation at ATAGI has recommended a COVID-19 booster shot be given to people who are severely immunocompromised. ATAGI says either the Pfizer or Moderna mRNA vaccine should be used for the third dose booster rather than the AstraZeneca vaccine. It says the booster dose should be administered between 2 and 6 months after the second dose of vaccine. The study shows a waning of immunity occurs between 5 and 6 months after the second dose for both Pfizer and AstraZeneca, and this waning is greater for older adults. And with Australian peak vaccination occurring back in August, waning immunity will be noticeable by around February 2022. And with many older people getting vaccinated early, especially those in residential aged care, it's felt they may now already be at risk without a third booster. The World Health Organization says more than 8 million people have been killed by the COVID-19 coronavirus, with over 4.9 million confirmed fatalities and over 240 million people infected since the deadly disease was first spread out of Wuhan, China. A new study warns that some 60% of the Antarctic ice shelves may be vulnerable to melt-induced cracks, which could trigger ice shelf collapse. A report in the journal Nature warns that global warming means more meltwater could flow into these cracks, causing them to grow larger through a process called hydrofracturing, driving ice shelf collapse. Ice shelves are floating extensions of ice sheets and can help slow the flow of ice into the ocean through a process known as buttressing. Allowing more meltwater to flow into the oceans would have major consequences for Antarctic mass loss and global sea level rise. A new study has found that the amount of energy rooftop solar systems could potentially provide is greater than the world's total energy consumption in 2018. The findings, reported in the journal Nature Communications, mapped out 130 million square kilometres of global land surface and identified some 0.2 million square kilometres of rooftops that could be used for solar panels. The authors calculated that these rooftops could generate 27 petawatt hours per year, with the greatest energy generation potential being in Asia, North America and Europe. The authors say it would cost somewhere between $40 and $280 per megawatt hour, with places like India and China being among the cheapest at $66 and $68 per megawatt hour respectively, Australia and New Zealand being around $90 per megawatt hour, and the UK and US being the most costly at $251 and $238 per megawatt hour. Meanwhile, a study by the CSIRO has found that converting to renewable energy would cost Australian consumers over $1 trillion. The findings mean every household power bill would need to increase by around $100 per month, and that doesn't include the transition for transport. At the same time, another study, this one by Stanford University, has found that the global transition to 100% renewable energy by 2050 would cost $73 trillion. The report, published in the journal One Earth, provides detailed roadmaps for how 143 countries, which account for 99.7% of global greenhouse gas emissions, could transit to 100% renewables by 2050. The analysis excludes the use of nuclear power, biofuels, or so-called clean coal. In the United States, the roadmap would require the construction of 288,000 new 5-megawatt wind turbines and 16,100 megawatt solar farms. But no word on what happens at night or when the wind stops blowing, as happened in the UK last week, forcing British power companies to import electricity from European coal and nuclear power stations at highly inflated prices. The study also didn't look at what the cost of battery storage would add to the bill, or the financial and environmental costs of the rare earths needed to produce them. Meanwhile, a new report by the Helsinki-based Centre for Research on Energy and Clean Air and the US-based Global Energy Monitor says the world's largest greenhouse gas polluter, China, which produces almost a quarter of the world's CO2 output, is currently building or planning to build 43 new coal-fired power stations and 18 new blast furnaces. That's equivalent to adding about 1.5% to China's current annual emissions output. At the moment, China produces more greenhouse gas emissions in 16 days than Australia does in an entire year. An alternative health practice promoting hyperbaric oxygen therapy and its clinical director have been fined a combined total of nearly $727,000 in the Melbourne County Court after one of their patients died. Hyperbaric oxygen therapy involves administering pure oxygen in a pressurized environment, with a heightened air pressure allowing a patient's lungs to gather much more oxygen than would be possible under normal conditions. But without proper medical supervision, the treatment can cause lung damage, a fluid buildup or a rupture of the middle ear, sinus damage, vision problems, and oxygen poisoning, which can cause lung failure, fluid in the lungs, or seizures. Tim Minham from Australian Skeptics says there are a very limited range of medical conditions for which the treatment is actually recommended.
There are people who are still sort of selling this hyperbaric chambers and things like that to sort of increase the amount of oxygen intake. They go into a chamber, which is, like a little phone booth type thing, and they pump a lot of oxygen in and you breathe in it because too much oxygen is not good for you. But this company had a customer who was suffering from, a long-term customer, so he'd been going for a while, who had multiple sclerosis and MS-induced epilepsy and a history of life-threatening seizures. So not a great person to put under stress, and apparently he was left on his own. Staff were not properly trained in how to look after him. They found him unconscious in this chamber, took him off to hospital. He died a couple of days later. Company's been fined $550,000. The owner, who's a former chiropractor, has been fined $175,000. So it's a significant amount of money, but nothing compared to the person who died, of course. But mainly the reason they've been fined is not because of the effectiveness or efficacy of oxygen treatment, oxygen therapy, but because the staff weren't able to look after him properly. So it's more an admin thing than it is a health thing. Now, whether people should then go and say, well, let's look at this whole concept of oxygen therapy, that's a problem area. That if you're looking at not training your staff properly is one thing, but not training your staff properly in an area of therapy which is probably uncertain, if I can put it that way, should be the real issue. So there's issues with the therapy itself, but in this particular case, fairly hefty fines applied because the work and safety processes within the company weren't up to scratch.
That's Tim Mendham from Australian Skeptics. That's the show for now. SpaceTime is available every Monday, Wednesday and Friday through Apple Podcasts, iTunes, Stitcher, Google Podcast, Pocket Casts, Spotify, Acast, Amazon Music, Bytes.com, SoundCloud, YouTube, your favourite podcast download provider, and from spacetimewithstuartgary.com. SpaceTime's also broadcast through the National Science Foundation on Science Zone Radio and on both iHeartRadio and TuneIn Radio. And you can help to support our show by visiting the SpaceTime store for a range of promotional merchandising goodies, or by becoming a SpaceTime patron, which gives you access to triple-episode commercial-free versions of the show, as well as lots of bonus audio content which doesn't go to air, access to our exclusive Facebook group, and other rewards. Just go to spacetimewithstuartgary.com for full details. And if you want more SpaceTime, please check out our blog, where you'll find all the stuff we couldn't fit in the show, as well as heaps of images, news stories, loads of videos, and things on the web I find interesting or amusing. Just go to spacetimewithstuartgary.tumblr.com. That's all one word, and that's Tumblr without the E. You can also follow us through @StuartGary on Twitter, @SpaceTimeWithStuartGary on Instagram, through our SpaceTime YouTube channel, and on Facebook, just go to facebook.com/SpaceTime with Stuart Gary. And SpaceTime is brought to you in collaboration with Australian Sky and Telescope magazine, your window on the universe.
You've been listening to SpaceTime with Stuart Gary. This has been another quality podcast production from Bytes.com.